Well, hello friends. Welcome back to Browser Hacking. Today we are going to continue working on the JavaScript bytecode stuff. So in the last video, we taught it how to create bytecode from simple addition expressions. So 10 plus 25, for example. And we can now run the JS engine. If we dump out the AST, of course, it looks like this. So you have a binary expression with 10 plus 25. And if we turn that into a bytecode and dump it, we get two loads and an add, which are the two bytecodes that we came up with last time. And we also have a way to run it, which then dumps out the register state of the interpreter, the bytecode interpreter at the end. So today we're going to continue on this work. And what I would like to do is add variables to the mix so that we can read and write variables in the current scope. So let's go ahead and create a new test, and we can do something very simple like foo is 5 and bar is, oh, you know what? Let's do something with strings maybe. Yeah, why not? F and bar is B. Let's do that. And foo bar is foo plus bar. Okay, so that is going to fall apart because we need to implement a bunch of things. So it says here, missing generate bytecode. Okay, so some new nodes that we need to handle are assignment expression. So we have an assignment expression that assigns f, string literal f, to the identifier foo. And we don't handle this node or this node. And the rest of the nodes are familiar. So I think string literal, we can start by doing something with that. So we will go to the AST. And by the way, if you did not watch the previous video, I'm kind of doing these in sequence. So I think it would make a lot of sense for you to go and watch the previous video where I start building the bytecode engine. So because I'm going to keep talking now as if you have that context. So we are going to go and add the generate bytecode for what was it? Assignment expression and string literal. So assignment expression, of course, you're assigning something on the right side to something on the left side. And there we go. And also to the string literal. Okay, and then let's go ahead and add some stubs here. So assignment expression, generate bytecode, la la la, and also for string literal, which I guess will be similar to numeric literal, except we can't just load a yeah, string literals are a little bit different. Because in the case of a value, it's just a numeric value, which is not allocated on the GC heap. But for a string, we need to actually like GC allocate a string object for that. So it can't just be a simple load. Rather, it has to become some kind of a create string thing. So let's see how we would do that. So generator emit like bytecode op new string maybe, or create string. Create string feels pretty straightforward. New string feels even straighter and forwarder somehow. So let's call it that. And where do we store that? I guess into a new register. And the string will be whatever our string value is in the string literal node. Sure. And then we'll just return that register. Okay. So let's add an op for new string. Public instruction, sure. Let's grab these here. And what does that op look like? Register destination and string, I guess. Yeah. Okay. And then we just have to keep track of these. So m destination and string m string. Yeah, that feels pretty reasonable. And then we also need the assignment expression node. So what are we going to do there? So assignment expression is a bit of a tricky one because it depends on what you have on the left-hand side. Now, in our case, we just have an identifier on the left-hand side because we're just assigning to a variable, right? But if you had something like, if you do something like o.foo, then the left-hand side of the assignment expression becomes more complex because now it is a reference to the property foo on object O. So that requires reference resolution. But in the case, let's focus on this case for now. And the way we can simplify is to just only handle that case. So I guess like if is identifier left-hand side, then do yada yada, otherwise to do, basically. Okay, and then let's say we'll just static cast it to an identifier. And then now we need to produce some kind of an instruction here. So I guess we want to set a variable. So how about we call it set variable? Generator emit bytecode op set variable. What should we call it? Like set scoped variable? Set. Let's just call it set variable for now, and then if it turns out that we need to distinguish between different set variables, then we can come up with better names later. So we want to set a variable, and the variable we want to set is the destination, and we're doing this Intel style, so the destination goes first. So that would be the identifier string. Does that make sense? Why is the syntax highlighting not working once again? Oh, okay, that's my bad. I wrote static instead of static cast. Although I guess I also need to declare set variable as a thing. So let's try to do this. Set variable. So here we have an identifier on the left-hand side, followed by a register that we are setting from. So the source. And then we just do something like this. Yes, and then all the basics. Call that source, and this will be a fly string since identifiers in libjs are always fly string because they are globally deduplicated. And you don't like that? Oh, because it's incomplete. Okay, and I think we can probably just put in a get variable while we're here, because it's kind of the same except the other way around. So get variable instruction has a registered destination, and it gets from an identifier. So same basic idea, just the other way around. And you don't like this because? I don't know why he doesn't like it. Dust. Okay, come on, what am I doing wrong? What is the obvious mistake I'm making here? Dust has not been declared. Oh, the comma. Okay, well that was stupid. I feel like that could, the compiler could kind of tell you, hey dude, you had the colon and the commas mixed up. Okay, so then we are instantiating this and that doesn't work out because we also need a source, right? So the source is going to be whatever's on the right hand side. So we'll do something like this. So the right hand side, just generate bytecode for it, no big deal. And then we'll just pass that in there. And I guess the result of an assignment expression should be whatever was on the right hand side, if I recall correctly. I think at least that's how the AST interpreter handles that. So here's assignment expression execute, the AST walk, and when we return right hand side result. Right. Yeah. Okay, I'm just gonna do a restart, try to get my syntax highlighting back. And what don't you like? Where are we? 2291. All right, take me to 2291. This is bad because set variable has a fly string and a source. And is this not a fly string? That is a fly string. Is that not a, ooh, that's an optional. Oh, I always feel like I always forget that generate bytecode returns an optional register. So we'll just do this for now. Has a value, and then poof. Taking some time here. Come on now. Don't be shy. And that didn't work out because, because I didn't implement those virtuals that I added. But not to worry, we can do that quickly. New string, toString. New string. And I guess we can print the string that will be instantiated. So mstring, no problem. And string is that. Sure, mdest. Maybe we should add a nice formatter for these registers so that we don't have to keep doing like r brace, but we could just do brace, and then it would print mdest. We'll do that after this. Oh, and we also did get and set variable. Get variable has a destination register and an identifier for the variable. And set variable has an identifier where the thing will go, and a source, which is a register that we get it from. So a little bit backwards. Sure. And then we also need execute implementations. So new string. This needs to like GC allocate a string. So new string is, or we'll just call it, we can just call it, maybe we'll call it new string. Interpreter, global object, we can't see into it. But basically we need to get to the heap here, so that we can allocate. Heap, allocate. Or no, we don't need to get to the heap. We just need to JS string. I kind of want to have an accessor for the VM here. I don't have it, so let's add one. Maybe we'll be nice and do this for quick access. It's not gonna hurt. Global object VM. Yeah, we'll do this. We won't regret doing that. Okay, so now we have a pointer to the VM. And should be good. There we go. And then we need to shuffle that into the destination register. So new string. In fact, maybe we can do that all in one go, just like that. Isn't it beautiful? That does look pretty nice, actually. Okay, and then get variable. And set variable. So set variable is interpreter. I know the VM has set variable, so then you just pass the name. So identifier followed by the value, which is a register. So source followed by the global object, followed by whether it's the first assignment. Okay, let's skip over those parts for now and just do bare bones set variable. And the same story with get variable that, let's see. So here we have a destination register, which would be interpreter reg. M destination is interpreter VM get variable. M identifier, interpreter global object. Okay. New string get variable, set variable. Very, very good. Will these nodes be enough? No. Missing generate bytecode. Oh, wait, I guess it's the identifier node here in the binary expression, because these need, yeah, right. They need to actually generate the get variable node. We only did set variable. So identifier needs to also have bytecode register generate bytecode kunst override generator. Okay. And what does that look like? Identifier. Okay, so now all we got to do is produce a get variable opcode and load it into some register that we return. So we'll just say reg is generator, allocate register. Generator emit, bytecode op get variable, save it into reg, and the name is mstring. And then return the reg. Let's try it. Okay, so does this... We can't actually see if the assignment succeeded, but we can see that set variable uses register 5 as a source, and register 5 does indeed contain the concatenation of f and b. So we know that the concatenation succeeded, which means that we created a new string just fine, assigned it to a variable, and then we were able to read out that variable and then concatenate those. This is actually kind of cool to look at. It's like an assembly language for JavaScript. It is interesting though. I wonder what is the there's so much redundant stuff that ends up happening here. Now, of course, we would do a lot of redundant stuff the way we currently do things with the AST as well. But I wonder, because I'm not super familiar with this type of stuff, so I wonder what is a good technique for figuring out that after you assign to foo here, for example, we don't need to refetch foo here because we already know that it's whatever is in R1 is still going to be there by the time we get here. Although, I guess that is actually kind of non-trivial because JavaScript is very dynamic, right? So you would have to be sure that no side effects happened between here and here. And that's probably extremely non-trivial. So yeah, I was thinking maybe you could apply some optimization here, but that's probably less straightforward than it seems. Anyway, we're definitely not going to start thinking about optimizing the bytecode right now. We are just looking to produce it and see that it can do the right thing. And it seems that it can, so that's really cool. Let's see. That's really nice. Okay, so let's commit some stuff. So basically we're adding some new opcodes and adding basic support for them. So, wait. Let's do this a little bit differently. Because I added the VM getter to interpreter, we can just do that separately. libjs. Add a VM accessor to bytecode interpreter. Yeah, that's just nice to have. Okay, and then let's commit these new opcodes. So JS add some more opcodes for the bytecode VM. So we're adding new string, get variable and set variable. These are the ones that we added, right? Yep. Okay, I think that would be pretty good. Allocates a new primitive string from the GC heap. Retrieves a variable from the current scope. In the current scope, assigns variable in the current scope. Okay. So let's try to make some other thing. What did I say before? Oh, right. Adding a formatter for this thing so we don't have to do this. Let's see. Let's do that right away. So register, it just needs format string thingy. So we'll copy that. When I'm doing stuff like this, I always copy paste something from somewhere else, which is perhaps not the most elegant thing in the universe, but it does work. So whatever. And then we will simply do R like that, value index, boom. And that should allow us to clean up all of these so they can just be like that. Should probably have done this from the get-go, but better late than never. Be a nice little improvement, and we'll have it going forward. So, doop, 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 doop. Yeah, they still come out correct. That's really cool. So commit A, Node.js, add formatting helper for bytecode register. Yeah, I mean that's just nice. Okay, let's I guess we can do some small things like let's implement a couple of more ops just to get the feel of it. So we had add. Let's do like sub, I guess. So we just copy add, make sub. Works exactly the same way, except when you execute and when you stringify, we just have to do something a little bit different. Sub, and instead of calling add, we just call sub. Boom. Okay. And let's make sure that we can subtract. What are some cool numbers to subtract? Let's subtract 11 minus 9. Cool numbers. And that didn't work out. Okay, so oh yeah, right, because we have to actually produce the subnode. So where do we do opt add? It was in here, binary expression generate bytecode. Yeah, so we have a binary expression, but now it has a minus op instead. So here we just need to do check for binary op subtraction instead. Also, I wonder, like, maybe we can just always allocate a destination register, and then we don't need to do that in each one, and we can lose the braces. That's kind of nice. So it would just be like that. All right, take your time. Okay, so this 11 minus 9 program produces 2 loads and then a sub, and the result register R3 at the end contains 2 as expected. Nice. Nice. Very nice. Okay, let's commit that. Add sub bytecode for values sub bytecode instruction. Subtract values. Yeah. Oh, there are so many different binary ops. But I mean, we have to do all of them, but we don't need to do all of them now. I think maybe this will actually be it for this video. I think we did some nice stuff here, so yeah, let's call it a day. Make a short one, and we will keep going with this. So as you've noticed, I'm trying something new here, like making a bunch of videos that I will then upload together to see how that's like. Something I haven't really done before. So if you enjoy this format, let me know. And if you're watching this much later, then maybe this doesn't make sense, but this was part of a set of videos that came out all together about the original bring up of the bytecode VM in libjs. So yeah, if you made it this far, thank you for watching, for hanging out. And I hope that you saw something interesting here. And I certainly find this very interesting. It's fun to just take these small steps into this new stuff. And we will just keep going with it. So I'll see you in the next video.